Hello, my name is Daniel Israel Kaku, and today I would want to go through the uniqueness of the heat equation using the energy method with you. And we will be considering a non-homogeneous heat equation with an initial condition, which is also non-homogeneous, and we may consider one after the other, a Dirichlet and a Neumann boundary condition, all non-homogeneous. So first of all, we would want to consider two different solutions to our non-homogeneous equation. So let U and V be two equations, and I'm making them very simple to make our solution compact since we don't have much space. So let U and V be two different solutions, and since they are two different solutions, it means they satisfy the equation there. So we may have UT minus KUSS to be equal to F. We may also have VT minus KVSX to also be equal to F. Now, since these two are solutions, by the linear principle, we could also say that W, which is equal to the difference of U and V, also is a solution and solves the PDE W T equal to, or let me put it this way, Wt minus K WSX equal to 0. This came as a result of F minus F from this expression. That is, we could easily simplify this expression, these two expressions. Finding the difference of these two expressions quickly give us this. As you can see, this minus this is equal to Wt, and this minus this is equal to minus K WSS, and F minus F is also equal to 0. So this gives us this, and we do the same on the boundary conditions. So from here we could also get the initial condition Wx0 to also be equal to 0, because we may end up getting it as f of x minus f of x this way, which is going to be equal to 0. Sorry, I could probably change this to be g of x since we have an f here, and come back here and make it g of x and g of x. Yeah, so this gives us the initial condition to be homogeneous, and that would be the same for our Dirichlet boundary condition. That is, W0t will eventually be equal to the second one, which is going to be WLT, and they will also be equal to 0. Now here it is assumed that the heat at both ends of the rod are going to be 0, and the initial heat at time 0 is also going to be 0. So the linear Cauchy problem we have is what we have here, and we have it as W solving that particular Cauchy problem. So what we want to do now is to consider this our new heat equation, which is Wt equal to K WSX. I've just moved this to the right hand side of the equation. We will now multiply through by W to generate this equation, and looking at the left hand side very well, we could easily rewrite it as the derivative of half W squared. That is, by finding the derivative of this, it quickly gives us what we have here. And repeating the left hand side, we could also take our time to find an expression of the right hand side. That is, should we find the derivative of WX, we end up applying the product rule to get in. That is, the derivative of this is WX. We already have one here, so that gives us W squared x plus, this time we maintain the W and we differentiate the x, giving us WXX. That is by maintaining the W, so W and WSX. Now from here, we can now see this expression as exactly what we have here. So by little substitution, we could generate the right hand side to be the integral, that is, let me finish this left hand side. We could generate the right hand side to be K times W, that is the derivative. I'm writing this WWS minus another K WX squared. So this expression has now been simplified into the expression we have here. Now we find the integral of both sides of the equation from 0 to L. From 0 to L, that is the distance of the rod from 0 to L with respect to dx, and also with respect to dx. Here we want to bring the derivative outside the integral, and this time it becomes a direct derivative, giving us the integral from 0 to L of half w squared dx, which is equal to, finding the integral of this. Now this constant k can also easily come behind the integral. So having the integral and finding the integral of a derivative with respect to x is the same as the integral and the derivative cancelling out. So we are just left with wx, which is being evaluated from 0 to L. And we have minus the integral, we can also write the k here, of wx squared dx. So from here, we just quickly evaluate the expression we have here. However, the evaluation of that expression, if I should just find the evaluation of this, remember from our boundary condition that w0t is equal to 0 and wlt is also equal to 0. So quickly, the evaluation of the expression here immediately goes to 0. Hence, the expression we are left with is the derivative of the integral of half w squared dx is equal to minus the integral of 0L with a k here and w squared dx. Now, understand that we could call the expression here E of t, that is the energy. So we can quickly indicate the left-hand side as the derivative of the energy, E of t, which is equal to minus k integral from 0 to L of w squared dx. From here, because w is always positive, the integral of that positive expression will always be positive. Now, given that k is always greater than, is assumed to be 0, we will have the expression at the right-hand side to always be negative. Hence, we can say that the derivative of the energy is less than or equal to 0. That is for t greater than or equal to 0. However, for t equal to 0, having the energy to be equal to the integral from 0 to L of half w. Remember, the full expression of w is wst this way, dx, with a square here. Now, having the expression this way and evaluating this at t equal to 0 gives us this expression here, w squared of x0 dx. Remember, however, that our initial condition we had is also equal to 0. So this whole expression here is 0. Finding the integral of a 0 value is automatically 0. So we also have that the energy at the initial time is also equal to 0. Now, looking at the energy itself, we could also see that differentiating the energy or finding the energy that is for t greater than 0 will always be positive, since the expression here is positive. So the sum of a positive expression or a positive value is always positive. Hence, we can easily also conclude that the energy is always greater than or equal to 0. Now, considering the three conditions we just had, which is the derivative of the energy is less than or equal to 0, we also just had that the energy at the initial time is equal to 0, and the energy itself is always greater than 0. We can deduce that the energy itself at all time is equal to 0. This expression implies that the integral from 0 to L of half w squared x is equal to 0. Remember, the energy we said is the same as the integral of half w squared. So from here, this is only possible because the expression half w squared is always positive. This expression or this answer is only possible if and only if W, which is WST in full, is equivalent to 0. That is the only time we will have the integral of the W squared to be equal to 0. However, from here we have assumed that WST is the same as the difference of U and V. So doing that substitution, we have UST minus VST to be equal to 0. And that can quickly be concluded as U is equal to V. So U is equal to V then implies that the solutions we assumed initially to be U and V as the solution of the heat equation are actually the same. And that justifies that the heat equation, the solution to the heat equation is unique. So we can conclude that the solution to the solutions to the heat equation is unique, since the two solutions we considered are equal. Thank you.